All right, so we worked on perimeter and circumference, both of which were measuring the lengths of segments and curves. And so now, instead of a distance, what we're looking for is an amount of space. So looking at area of polygons. You should not have any difficulty whatsoever with exercise 1. We have a rectangle. We know that a rectangle can be determined by just calculating length times width. So if I go to do the area of this rectangle, it is simply going to be 8 times 5, which gives me 40 centimeters squared. Okay, not even going to spend any more time on that. The area formulas for parallelograms and triangles. Another thing that you're familiar with, parallelogram formula does require you to drop an altitude down from a vertex. So that can often be outside of the parallelogram, or it could be within the parallelogram, but it must make a right angle with whatever you're using as your base. If you were to turn this parallelogram and use the other side as your base, that's fine, but then again, you would need to drop a perpendicular to that base. Same thing with triangles. You need a perpendicular to a base, which sometimes is one of the sides of the triangle if it's a right triangle, and sometimes it's outside if it's obtuse, or it could be inside as well. So we have those two formulas to go off of. We're looking at exercise 2. A patio is to be made in the shape of an isosceles triangle. And the calculation given here is 1/2 22 times 16. This is a common mistake, and that's why this problem is here, is that sometimes students will look at the side of a triangle and just use that as the height. If it's not perpendicular to the base, then it's not the height. So the 22 is not the altitude of the triangle. That needs to be calculated another way. So if I'm trying to find the area of this patio to the nearest square foot, it would be nice to know what this height actually is. It splits the base into 2 equal segments. And so I can just simply do Pythagorean theorem to solve for that. So the height squared plus 8 squared is supposed to equal 22 squared according to Pythag. And so the height comes out to about 20.5. So to do the area, I could say 1/2 base 16 times height 20.5. And that's approximately 164 feet. Now there is another way you can solve for the area of a triangle when you have all 3 sides labeled but no height information. You can use what's called a semi-perimeter. So the perimeter of this triangle would be 22 plus 22 plus 16, right? And that comes out to a total of 60. But the semi-perimeter would then be half of the perimeter, which would be half of 60 or 30. Formula using the semi-perimeter goes like this. You say that the area is equal to the square root of the following product. It's semi-perimeter times semi-perimeter minus A times semi-perimeter minus B times semi-perimeter minus C, where A, B, and C are just the sides of the triangle in any order that you want to, because you're going to end up using them all and subtracting anyway. So if I follow through with this, S is 30. In the first grouping, it would be 30 minus any side you want. So let's say it's 30 minus 22. If I do 30 minus 22, I get 8. We'll call side B the other 22. So it's another 30 minus 22, another 8. And then the S minus C would have to be the side I haven't used yet. 30 minus 16 is 14. All right. And if I just multiply all that out and do the square root, the area comes out to approximately 164 again. These should be squared, actually. I should put a square on this one too. So if you have a side triangle, this is an option for you. It doesn't have to be isosceles. It could be any triangle with all 3 sides given to you. This semi-perimeter formula might be helpful to you. Okay, so if the patio is covered by stone, that costs $12.25 per square foot. All we need to do is multiply. Cost is $164 for the square footage times 12.25, and that is about $2,009. Okay, so moving on to the next set. So if we are working in the coordinate grid, we have some tools that we can use. So parallelogram ABCD has the following vertices at A, B, and C. We just need to figure out where D is. So what I would want to do is take this horizontal segment AB and duplicate it down here at the same length. From A to B is a distance of 9 units. So from C back to D would have to be 9 units as well. And that would be parallel as well. So equal and parallel forces a parallelogram. So my coordinates are -3, -2. There are other places that D could go to make a parallelogram. They just wouldn't be on this grid. So it could go out here, could go up here, but this is the one that fits on the grid. All right. So to determine the area of this parallelogram, what I want to do is let's just use one of these segments as the base. So segment DC could be the base. And then if I drop a perpendicular to it, it would be like that. So it looks like my base is 9 units. It's base times height. So for this parallelogram, it's 9 units times the height, which appears to be 8 units. So that's going to be 72 units squared. Which is the longer side, AB or BC? Well, we can do distance formula to determine that. AB I know is 9 because I can just count it. But to do BC, it's going to be, let's see, vertical distance is 8, so it's 8 squared, and horizontal distance is 3. Yeah, it's a 3 by 8 distance, so 3 squared. So I have 64 plus 9, total is 73. That square root is less than 9, and so AB must be longer. All right, so we have all of that. And so sometimes we also get some trigonometry involved. So an isosceles triangle shown below, legs are 10, vertex angle is 46. Just remember that vocab because that's going to come up a lot. Legs, vertex. I want to find the area of the triangle. All right, so we are going to first try to find the height of this triangle. Split it right down. And that makes these angles now 23 each. And so if I want a trigonometric ratio for the height, this height is acting as the adjacent side to the 23. So it's going to be cosine 23 equals h over 10. Leave unevaluated. So that means I don't want to put this in my calculator. H is simply 10 cosine 23. All right, now to find an expression for involving a trig ratio for the length of the base. For the base, I think what I want to do is first treat each of these as x, and then what I'll do to get the base is just double whatever I got for x. All right, so with this triangle here, x is the opposite side from 23, so sine 23 is equal to x over 10. And so x is 10 sine 23, which means that the base must be 2 times 10 sine 23, or I could just say 20 sine 23. And that's also been left unevaluated. So finally, to determine the area of the isosceles triangle to the nearest square inch, it's 1/2 base times height, or 1/2 times base 20 sine 23 times height 10 cosine 23. All of that comes out to approximately 36. Do we know a faster way to do this? I think so. If we remember back to our trig unit with oblique triangles, triangles that don't contain a right angle, we can also say that the area is 1/2 xy sine theta. That's a faster way to do this problem. X and y would be the side lengths surrounding the angle, so I'd have 1/2 times 10 times 10 times sine 46. If you put that into your calculator, you are also going to get approximately 36. So faster way, this one was guiding me through the process of establishing the height and the base, but if you want to use your old methods of oblique triangles, that's also perfectly acceptable.